Hi guys, welcome back to the channel. We'll be continuing our discussion about file I/O. In the previous video we already talked about FD, that is file descriptors. We talked about read and write system call, and towards the end we talked about close and lseek calls. I'll leave a link to this video somewhere on the top so that you can revisit these topics. In this video we are going to proceed further in file input and output. We are going to talk about buffering that Linux provide in order to fasten up the read and write calls. We are going to talk about kernel buffering and the standard IO library buffering as well, that buffers all the data when we call library functions for input and output like f get c, f get s, printf. We'll also touch upon an important concept about kernel space and user space. We'll see what is a user space and how we switch from user space to kernel space with the help of system calls. So without wasting any further time, let's get started on this one. Before we talk about buffering, we need to understand where these buffers lie. For kernel buffering, the buffer lies in the kernel space. For standard IO library buffering, the buffer lies in the user space. We need clear distinction between kernel space and user space in order to understand buffering concepts. User space is the space where the memory of the program is set up. Stack section, heap section, data segments all reside in the user space of the program. Even the static and the shared libraries also reside inside the user space. We'll talk about static and shared libraries in one of our future video. Whenever this running program invokes a system call, it has to switch from user space to kernel space. Kernel space is a restricted area that only kernel can access. A user program cannot access the kernel space directly. It has to invoke a system call to switch from user space to kernel space. Kernel would then implement the system call using a kernel stack and return the output of the system call back to the caller in the user space. This distinction is important because user program should not be able to access system resources directly. Only the kernel can access system resources like disks, RAM, and the user program has to rely on the kernel when it wants to access these system critical resources. This is a detailed diagram as to how a program switches from user space to kernel space. This is the application program which contains the code that the user would have written. This is the function that it is trying to invoke. We have already talked about exec system call in one of our previous video. I'll leave a link somewhere on the top so that you can revisit. But actually exec is a standard C library wrapper on top of the actual system call. All the library functions are implemented and run in user space itself. When the application program invokes exec VE, there is a new stack frame that gets set up. This exec VE function makes sure that all the arguments required for the actual system call are copied into the appropriate registers. It then invokes this instruction. We formally call it a trap instruction that causes a switch from user space to the kernel space, and these trap and the arguments for the trap instructions are all the arguments for the function along with the identifier for the system call. Once this trap instruction is executed, the control switches to the kernel space now, and the system call is executed here inside the kernel stack. If this system call invokes multiple functions, each of the function would be set up inside the kernel stack. The identifier that was populated as part of the argument inside the wrapper function is used to invoke the actual system call, which is depicted over here. This would either return an error or a positive number in order to indicate a successful completion. This return value unwinds the kernel stack frames, and the top level system call, when unwinds, returns back to the user space wrapper function. If there is an error, this wrapper function would update the global error variable and return to the actual program. So when we say kernel buffer, it is a buffer that lies somewhere inside the kernel space, and the user program has no access to the kernel buffer. And whenever we say a user buffer, this buffer lies in the user space, and and the memory for this user buffer is reserved by the program itself. Let's now jump back to the original topic of buffering. There are two kinds of buffering that is provided. One is kernel buffering and the other is standard IO buffering. Kernel buffering happens with the help of a buffer that resides in the kernel space, and standard IO buffering happens with the help of a buffer that resides in the user space. Whenever you invoke a write system call, the data is not actually written to the file. The write system call merely enqueues the data to be written into a kernel buffer, and once the data is copied to the kernel buffer, the write system call returns back. It doesn't wait for the data from the kernel buffer to be written to the file that actually resides on the disk. With this design, the speed of write improves. It doesn't have to wait for the data to be written to the actual file. This is because disk access is costly. There is a lot of latencies involved with accessing the disk. There is a rotational latency where the disk head has to move to the appropriate sector and then the appropriate track and then write the data into the file. That is why when we invoke a write, it merely enqueues the data into the kernel buffer and waits no further for the buffer to be written into the disk. It now becomes the responsibility of the kernel to write whatever is present in the kernel buffer to the disk whenever the kernel sees this operation to be fit. Similar to kernel buffer, there is a second level of buffering that happens within the user space itself when we invoke IO functions from the standard IO library. These functions could be printf, f get c, f get s. Since this buffering is happening inside the user space, it is possible to buffer this data that has been allocated explicitly by the programmer. You'll understand this point once we look at this function call. This is the function that is defined within standard io.h, and it controls the behavior of the standard IO buffering. As you can see, it has 4 arguments. The last argument is the size of the buffer that we want to employ in order to buffer the data, whatever is being written or read. Mode is used to control the kind of buffering that we want to achieve. There are 3 kinds of buffering that we'll talk in just a second. This is the actual buffer where all the data that has to be read or written is buffered into. This is a file stream pointer, which is nothing but a wrapper over the file descriptor and various other attributes related to the file. Since file stream is just a wrapper over the file descriptor, it is possible to retrieve the actual file descriptor from the file stream and vice versa. These are the 2 functions that are defined within stdio.h, and they are used to interchangeably get either the stream or the file descriptor from one another. File no is passed the stream pointer and it would return me the file descriptor. Similarly, fd open is passed the fd and it returns the file stream pointer. There are few important things to note about set vbuff. The buffer that is being provided is null, then it becomes the responsibility of standard IO library to allocate a buffer and use it for buffering. Otherwise, if this buff pointer points to some memory location, then that memory location is used for buffering, and standard IO library in such case does not allocate any buffer. It is also important to keep in mind that this buffer should lie on the heap section. Otherwise, if this buff lies inside the stack frame, then there are chances that the stack frame unwinds and the memory pointed to by buff becomes invalid. Let's also talk about the mode argument. There are 3 kinds of buffering that is offered by the standard IO library. IO nbuff indicates that no buffering has to be done. IO lbuff indicates that the data has to be buffered until a new line character is encountered. We call such kind of buffering as line buffered. And IO fbuff is the default buffering behavior where the data is buffered until the buffer becomes full. By this, what I mean is, if this is the buffer in the user space, we usually set the buffering mode in the start of the program. So all the standard IO functions that lies after this set vbuff follows the buffering that has been set using this call. So for example, if we have set IO lbf, if we have invoked the fputs first with this abc string, and then we have invoked a fputs with zxy and a new line character, then by the end of first call, the buffer would have abc inside it, and by the end of next call, since there is a new line character at the end of this string, the data would then be moved from user space to the kernel space inside the kernel buffer. And the kernel buffer would then contain A, B, C, Z, X, Y, and a new line character. And this buffer would be emptied out for new incoming characters. Similarly, if we would have set the buffering mode to IO fbuff, then the data would be buffered inside this user space buffer till this buffer becomes full. And this is the size of the buffer that we use. For example, this is 10 bytes, then we are going to buffer 10 bytes and then flush them into the kernel buffer once all these 10 bytes gets exhausted, and clear out the characters for the new incoming data. IO nbuff disables any buffering. If IO nbuff has been set, then the data is transferred directly to the kernel buffer on call of standard IO functions. This is an example that I have added here to buffer any data that is written to standard out. Flush is also an important function which flushes the user space standard IO buffer directly to the kernel space. In a way, this overrides the buffering mode. So for example, if we have set the buffering mode to full buffering and the buffer is still not full, it has some space, and if flush is invoked in such state, then this buffer is flushed immediately to the kernel buffer and it is then emptied out for future function calls. It is also possible to control the kernel buffering, but the control is not as fine-grained as for standard IO library, where we had multiple modes for either full buffering, line buffering, or no buffering. Here we can either enable the kernel buffering or disable the kernel buffering. Fsync is a equivalent call to flush. Fsync flushes the kernel buffer to the disk, whereas flush, as we discussed in the previous slide, would flush the standard IO buffer into the kernel buffer. This is a good explanatory diagram that explains all kind of buffering that we have discussed until now. Let's follow the flow. A printf has been invoked and the data then gets buffered to the standard IO buffer. If we invoke a flush, the data is then written to the kernel buffer. The data would also get written to the kernel buffer on encountering a new line in case of line buffered, or if the buffer gets full in case of full buffered, and it goes into the kernel buffer. Fsync system call is used to flush the kernel buffer into the disk. This is where the actual write happens. If we don't invoke fsync, then it is up to kernel to decide when it is going to initiate the disk write. We can disable the buffering altogether using setBuff call. This is one way of disabling the buffering, or we could use the IO nbuff mode as well to disable the standard IO buffering. In such scenario, the data doesn't go into the standard IO buffer and directly moves into the kernel buffer. We can also disable the kernel buffering by using a osync flag when opening the file descriptor. Whatever is written to this file descriptor is then written immediately to the disk, and this remains valid for all the writes that happen on this file descriptor after this open call. So if there are 3 writes that are happening after this open system call, then all the writes would block until the data is written to the disk. Let me also talk about an important scenario where, for example, I have invoked a write on a file from user space. This file actually resides on the disk. Let's call this file T1. This write immediately enqueues the data into the kernel buffer and returns back. The data is still not written to T1. If in such state another process comes and opens T1 in its own address space and reads the contents of T1, then it will still see ABC as part of T1. This is a optimization and abstraction that kernel performs, where instead of reading from the file, it has read the data from the kernel space buffer of a different process which has invoked a write on this file. So in this scenario, even when the data is not written to the file is reflecting the correct content when it is opened by some other process.